everybody. My name is Brent Pappas. I'm a PhD student at the University of Central Florida, studying under Dr. Gazzillo. And today I'm excited to be talking with you all about macros. So, again, the C programming language is unsafe. It provides no static safety guarantees, making it extremely easy for developers to write memory unsafe code. In fact, it's so easy that in 2023, the Cyber Information Security Agency reported that at 46% of its common weakness enumerations were due to memory safety errors. And the teams behind these projects reported that at least 65% of all their bugs were due to memory errors as well. And it's gotten so bad that in February of this year, the US government felt the need to publish a press release urging developers to write safer code, specifically calling out C and C++ as unsafe languages to be programming in. Now, when you think about it, though, it's kind of ridiculous that we're still facing this problem in 2024. I mean, isn't language safety a solved issue? We have safer languages now, like Rust, Kotlin, and Go. So why aren't developers using them? Well, the short answer is technical debt. If you look at the Linux kernel, Microsoft Windows, Apple Mac OS, each of these programs consist of millions of lines of C and C++ code. So telling a developer to just rewrite these programs in Rust is not really a viable option. And before one of you suggests that we use ChatGPT to do it for us, I hate to break it to you, but the machine learning technology is just not there yet. Even if you could just tell ChatGPT to rewrite the kernel in Rust for you, the output would contain so many hallucinations and mistakes that it wouldn't be worth your time to fix them all. Now, thankfully, there's an ongoing area of research into automated language translation that could solve our problem. One example, just as an example, is a tool called C to Rust for translating C code to Rust code. Unfortunately, there are a number of problems these tools still have to contend with. Just as an example, for going from C to Rust, memory management, so C programs manage their memory manually, whereas Rust programs manage their memory automatically via the borrow checker. C programs let you use unsafe raw pointers for things like pointer arithmetic, whereas Rust programs force you to use safe references, which do not allow for pointer arithmetic. And before you can even get to these two cool semantic analysis problems, you have to deal with macros. So C programs let you use the C preprocessor, which has its own unique macro system, whereas Rust programs have not one, but two macro systems, which are incompatible with C preprocessors. And I'm going to be focusing on macros for the duration of this talk for a few reasons. As I just said, they're the first issue you must deal with. Before you can get to these cool, again, semantic analysis issues, you have to deal with macros. And if you look at the repositories for C to Rust, 3C, which is a translation tool from C to check C, a memory safe dialect of C, these translation tools have issues that are open and have been open for several years relating to macros. And they're not going away anytime soon unless somebody actively tries to solve these problems. And also, I would like to complete my dissertation in a timely manner. I find all these problems really interesting, but I would like to graduate in 2 years, so focusing on macros for now. Now I'm going to go into an example describing why macros actually provide a problem for translation tools. Let's say you have some C program and you define a macro in it which accepts an argument A and expands to that argument, and then we invoke it with some argument X. Well, in the ideal world, we could run C to Rust on this code and have the following output where the macro definition is translated to a function definition, and the macro invocation is translated to a function call. This would be great because our abstractions have been preserved in the translated Rust code. But unfortunately, this is not what happens in the real world. In reality, C is not the same as a C preprocessor, so C to Rust does not know how to translate it. So the state-of-the-art approach that C to Rust and all other modern language translation tools take is to not even solve the problem, but just avoid it. And they do this by preprocessing the code first. This wipes away the macro definitions, expands the macro invocations, and in this case, all we're left with is a single variable x, which is not very informative, and in translated code, all you get is that little variable x. And this is kind of horrible, because now our wonderful abstractions and definitions are totally gone. Now, what if there's a way to solve this problem? What if we could extract the syntax, in other words, the structure of the original macro definition and pass it to our translation tool as well? Perhaps our tool could then reconstruct the macro as a function definition in the resulting code. And again, we're doing this all at a syntactic level, not using any semantics. This would be cool because, again, our abstractions are preserved. Unfortunately, this is not going to work either in all cases. To show why, let's see what happens if we change our definition of foo to be A++ instead. Now, in our preprocessed code, we would have X++. And let's apply our trick from before, extracting the syntax, passing it to C to Rust. The result would be the following code on the right, which looks innocent enough, it looks correct. We have the mirrored syntax of our original macro definition, but this is actually a wolf in sheep's clothing. This translation is totally wrong. If we look at the middle code here, the preprocessed code, we're incrementing the value of x in the environment in which it was passed to the original macro invocation. However, on the code on the right, in the translated Rust code, we're now incrementing the value of a local variable a. We've actually broken the semantics of our program, which is horrible. And what's really scary is that in the course of our studies, we found that for more than half of all macros for which it appears that a syntactic translation alone would suffice to translate them, that is actually not the case. So there is a way to potentially fix this. Instead of just passing the syntax to our translation tool, let's also extract and pass the semantics. And we can get this from the abstract syntax tree in the preprocessed source code. Then our tool could perhaps automatically translate our code in a more intelligent way, preserving the macro behavior and abstraction. In this case, by translating the argument A to a mutable reference. Now, this leads me to my key insight. If the reason that translation tools, automatic translation tools, cannot translate macros is because they do not understand them, then the solution is to just tell them how they work, providing them with both the syntax and the semantics of macros so that they can correctly and intelligently translate them to target language constructs. And again, just as an example, here, Rust. Now, I want to make it clear, in this work, we're not actually doing any automatic translation. That is for future work that I'm very much looking forward to doing. In this work, we're focusing on the analysis, extracting that syntax, extracting those semantics, because there's a lot of hard work that goes into that, and a lot of cool insights that come out of it. Now, I'm going to go into the first of the contributions to this paper proper. We have broken down macro, syntactic, and semantic behavior into 26 fine-grained properties. With these properties, we've actually composed them together into 6 different categorizations, into a macro analysis framework. With this framework, we were able to identify 2 kinds of macros, those that are easy to translate and those that are difficult to translate. Now, we've actually applied this framework by hand to show that it is a good tool for differentiating between hard and easy to translate macros. And we found that in real-world code, in our benchmarks we used, difficult to transform macros took us about almost 7 minutes to translate each. Easy ones took less than a minute each for about an 8 times improvement, which lends us some confidence that our tool is good, our framework is good for differentiating between easy and hard to translate macros. Now, we've actually also applied our framework to manually turn macros in the Linux kernel into functions. We submitted patches to maintainers to transform 11 macros into C functions. And in the end, maintainers accepted 9 of our patches, or 9 of our macro changes. They rejected 2 of them just for stylistic reasons. In those cases, the maintainer just preferred the macro. And along the way, we weren't even trying to do this. We actually discovered an integer overflow error in the kernel. One of the maintainers pointed it out to us when we were doing our translation, and we fixed it and made the kernel just a little bit better. We've also implemented our framework as an automated analysis tool. We're calling it Maki. We've ran it on a benchmark of over 86,000 macro definitions across 21 real-world C programs to identify properties of macros in real-world C code and find usage trends. And we've actually hand-checked the output of this tool against a statistically significant sample, giving us a 94% confidence or level of accuracy, giving us high confidence in our results. And we found that over a third of all macros were actually easy to translate, those cheap macros that I showed earlier, which is really exciting because that's way more than prior work actually suggested. And I want to talk about prior work. So there's no tool that does exactly what Maki does, analyzing the translatability of macros. But there was one tool from 2004 we were able to find that would not just identify easy to translate macros, but also translate them. This is by Many and Clark. So to compare our tool to theirs, and I want to make it clear, this tool is only able to translate a very limited subset of macros. Macros that could be translated to C variables. That's it. So to compare our tool to theirs, we actually ratioed the number of easy to translate macros they would find to the number of easy to translate macros that our tool, Maki, is able to find. And we actually find twice as many easy to translate macros on average than they do. In the best case, we find 7 times as many. And what's really neat is that this best case here is for Perl, and in the Perl code base, only 18% of its macros were easy to translate. That's a very low proportion of macros compared to our other benchmarks, which suggests that as the complexity of macro usage in the program increases, our ability to identify easy to translate macros also increases as well. And that concludes our presentation. If you have questions, please raise your hand and I'll answer them now.
Good. Any questions?
So, I'm not sure if this corresponds to your definition of easy and hard, but essentially macros are used in 2 ways. Straightforward macros, what I would call straightforward macros, and creative use of macros.
Yes.
So I suppose that creative use would correspond to your hard, but then it wasn't clear to me whether do you fully cover all creative uses of macros.
Excellent question. So actually I have slides to answer that.
So there's also some bad users of macros, which maybe if you don't handle them well, you can just go by the preprocessor route.
Yes. So there are some macros that are used very creatively, as you said. All of our properties cover all the macros. There is no macro that is left uncategorized or unclassified by all of our properties. So they are complete in that sense. And in terms of defining easy versus hard to translate, we define easy to translate macros specifically in the paper as ones that only require changes to the macro definition, the call set arguments, or declaration order of variables in the program in order to translate them. Whereas hard to translate macros are just everything else. So that's how we actually define macro translation.
Okay. Any other questions?
Well, let me give you. Let me have one question. So, not just translating C to Rust. Can you apply this technique to C to C? I mean,
Yes. Yes. So for the manual translations, we were doing C preprocessor macros to C. The idea is to not. One of the reasons why we're not doing the translation and the analysis all in one is to provide the analysis results to any downstream translation tool, so they can choose how they would like to translate using that information. So in Rust, as I said, they have their own macro systems. Maybe somebody would want to translate C macros to Rust macros. So that's why we provide just the information alone so that people can decide how they actually want to do the transformation.
Okay. Any other questions? Okay, let's thank the speaker.